Hey everybody, welcome back. So today should be the last video, and we're going to be talking about change of variables, a really awesome subject. So really quick before we get into that, let's go ahead and recap. So remember that when we changed coordinate systems to evaluate an integral, this introduced a certain factor into that integral. So remember, if we were doing polar coordinates, we had to multiply by an r. If we were doing cylindrical coordinates, we also multiplied by r. And if we were doing spherical coordinates, we had to multiply by rho sine of phi. Okay. Now remember, this was resulting from doing a transformation. It was coming from taking a shape and then changing it into another shape. Okay, that had more. It's basically taking a rectangle and changing it to something that's not really a rectangle. So today we're going to consider a general change of variables and how to calculate that extra factor for integration. Okay. And we'll see why we would want to do that later. So suppose we're computing a double integral and let x equal x of st, y equal y of st. So this is our change of variables right here. Okay, now I know this is kind of arbitrary, but think about this as going from polar coordinates, for instance. Like we're letting x be our cosine of theta, y equal our sine of theta. So that's what we're doing here with these equations. Okay. So like I said earlier, and like we saw earlier, whenever we do a change of coordinates, okay, and change to this new coordinate system, what's going to happen is we're going to have to introduce a different factor because areas are going to be a little bit different. Like we're sort of seeing in this picture here, we're going from a rectangle to something that's not a rectangle. Okay. So this is sort of the broad strokes. Your book goes into this very carefully and detailed, but again, I'm just going to sort of give you the broad strokes of how we come up with this. So again, suppose that we're taking a rectangle and we're changing it into some other thing, and we're going to suppose that this transformation leads to this shape here. That's again that's not necessarily rectangular. So the idea is, okay, we're going to be converting this double integral into, I'll call it d prime, okay, so the transformed domain, f of whatever this function is, x of st, y of st, okay, and then we're going to have to somehow convert this into ds dt, okay, in some way. So the question becomes, well, how do you deal with our differential there, dA? How does that relate to ds dt? Okay, so dA was coming from this side. Okay, remember it was kind of like our area of our rectangles. And now how do we interpret that in terms of this new crazy area? So the general gist of it is what we're going to do is we're going to estimate this area using a parallelogram. Now, I know you might be like looking at this picture and saying, hey, we're missing a lot of this. Well, remember that when we compute an integral, there's a limit there, right? And the limit is making the number of rectangles go to infinity. So as we let the number of rectangles go to infinity, this parallelogram is actually going to be a better approximation. Okay, so just keep that in the back of your head. I know it looks like we're missing a whole ton of area there, but when we take the limit, it'll be okay. Now remember from, I want to say it was a couple weeks ago, sort of the beginning of the class, remember that the area of a parallelogram, which is what we have right here, is equal to the length of the cross product V cross W. Okay? So that's one thing you need to remember. Now the other thing, and this is where the technical bit comes in, what is a good vector v and w that will estimate this area? Well, it turns out that v can be thought of as the vector partial of x with respect to s, partial of y with respect to s, 0, and we're adding a 0th coordinate so that we can actually take this cross product here, and w is equal to similar dx, but now we're going to take the partials with respect to t. Okay. And so the cross product of these two vectors is going to give you dx ds, dy dr, minus dx dt, dy, I'm sorry, not t, why did I say t? Oh no. Why did I say r in the beginning? Let's go back. This should be dx ds, dy dt, there we go. Don't look. dx dt, dy ds. Okay. And if you're not convinced of that, just take the cross product of these two vectors and you'll see you'll get this quantity. Well, and take the length. You'll see that you get this. Okay. So, again, just to reemphasize, we're estimating this crazy new shape with the length of the cross product, or the area of this parallelogram here. And this length here is what's going to be that extra factor when we do our change of coordinates. The quantity we saw, dx ds, dy dt minus dx dt, dy ds, so this thing right here, this has another name which we call the Jacobian. Okay, so given two change of variables, let's say, or given our change of variables, then we define the Jacobian, which we write as delta xy over delta st. And again, it's basically that cross product there, although we're going to see a different interpretation of this soon. So, summarizing then, if we want to do a change of variables, okay, go from this region to this region, then we do our substitution. We let x be whatever functions we get from our change of variables here. And then we have to multiply by the absolute value of the Jacobian, okay, which again is that mixed partial product sum that we had. Okay, so let's look at an example of why we would actually want to do this. So suppose that we're trying to evaluate this nasty thing right here. Okay? So the integral from 0 to 2 of the integral of x over 2 to x over 2 plus 1 of this nasty looking function here. Okay? So, and what we're going to do is we're going to do this by using the following change of variables. X is equal to r, y is equal to r plus s over 2. And then because we're going to need this in a little bit, this means that r equals x, just because we just flip that equality there. And then sort of solving for s in this equation, we'll get s is equal to 2y minus x. Okay, so let's see how we change variables, and actually we'll see why we want to do this. So like we would do with any double integral, what we're going to do is we're going to first sketch the region we're integrating over. Okay, so let's see, y is going between x over 2 and x over 2 plus 1, and x is going from 0 to 2. So let me mark that first. X is going from 0 to 2, and then x over 2 is just the line with slope 1/2. So let's say this is 1. Okay. And then let's see, x plus 1 over 2 is the line with slope 1/2, but y-intercept 1, so it should be parallel to this like this. Okay, so this parallelogram here, this is what we're seeing, and actually just for our convenience, I'm going to go ahead and put the points here. That's 2, 2. This is going to be 2, 1. The origin, 0, 1. Okay. All right, so that's the region that we're integrating over in this case, is this parallelogram looking thing. Okay. Now, if we make this change of variables, if we do this substitution, r is equal to s, s is equal to 2y minus x, or in other words, x is equal to r, y is equal to r plus s over 2, then what this is going to do is this is going to change this region. So let's see what happens to this region under this transformation here. Okay, so what we're going to be doing, and this is why I solved here for r and s, to figure out what happens under this transformation, what you do is we're just going to plug in all of our vertices into our transformation here. Okay, so over here I just want to remark this is the xy plane, and when we do this transformation here, we're going to transform this parallelogram into something in the RS plane. Okay, so let's see Let's see what happens here. So if we plug in 0, 0 into our equations here, we'll get 0, 0. If we plug in 2, 1, we're going to get 2, 0. If we plug in 2, 2, you'll see that we get, let's see, 2, 2. Well, that's really nice. 1, 2. And then if we plug in 0, 1 here into our equations up here, we'll get the point 0, 2. Okay. And notice what do we have here? We now have a nice rectangle. Okay. So hopefully you see right off the bat, one, it took this parallelogram, which is not as nice. It's not a horrible region, but it's not as nice, at least in terms of integration, and it converted it into a rectangle, which we know Fubini's theorem is all over, right? Additionally, if we look at our function that we're integrating, that nasty function, let me go ahead and erase some of this. Okay, notice we have 2y minus x appearing, and if we look at our change of variables here, that becomes s. So when we do this substitution, we're actually going to get a nicer function to integrate. So here's an example of where we're integrating over a slightly messed up region, and we're integrating a pretty nasty function. There's no real saving grace for that thing. And if we make this substitution, one, it's going to change our region from this slightly nasty region to a very, very nice rectangle. Sorry, I'm just marking the s-axis there as 2. And it's going to make our integral a lot nicer. Okay, so that's what's going to happen with the transformation. I wanted to give you this visualization. Whenever you do a change of variables, you do have to figure out what your new region is going to be, because that's going to help us with our bounds. But now let's go ahead and make our substitutions and integrate this. Okay, actually, let's go back really quick for a second. So now that we have this rectangle, notice that r is going from 0 to 2, and s is going from 0 to 2 as well, because we have this nice little rectangle here. Nothing too crazy going on. So that means that when we convert, okay, I'm going to put double integral of old. So when we convert, we're just going to have 0, 2, 0, 2 here. Very, very nice. Okay. Now let's deal with the function here. Okay. So x is going to become r. Okay. And y is going to become r plus s over 2. And so what that does is that's going to change this function here into r to the 5th. Now remember, whoops, I know that looks like r times 5. That should be r to the 5th. 2y minus x, that becomes s. And then e to the s squared. Okay, so we get r to the 5th, s, e to the s squared. Okay. Now again, so we've done our transformation, we figured out our new bounds. Okay. Don't forget to multiply by the Jacobian. I used to do this all the time as an undergrad. And in fact, when I did this problem a couple hours ago, I actually forgot to do this as well. So remember, when you do your change of coordinates, okay, or change of variables, you do have to multiply by that extra factor, right? Because we're changing the area. So that extra factor, again, is the Jacobian, the absolute value of the Jacobian. So let's figure that out. Let me go ahead and erase because we don't need these pictures anymore. So what is that Jacobian? Okay, so we're going to do dx dr dy ds minus dx ds dy dr. Okay, so dx dr, that's just going to be 1. dy ds, let's see, if I take the derivative with respect to s, we're just going to get 1/2. Uh-oh. Okay, minus dx ds, that's going to be 0 times, well, it doesn't really matter what dy dr is, that's going to be, well, it'll be 1/2, but in any case, that's going to go away, so we just have 1/2. Okay. All right, so then our Jacobian in this case is just going to be, or the absolute value of the Jacobian